All right, now we are going into the final mind map of solid mechanics. There are just a few last concepts to cover. Everything over the course of the class will be covered here except for column buckling, as we have not yet gone over that topic. So in black, just to help separate it and only go over the new concepts that I didn't cover in concept maps 1, 2, and 3. In black, we have lectures 1 through 14, and then starting with lecture 15, we have the new content. So in pink, from lecture 15, we will be discussing Moore's circle. In green, from lecture 16, we will be discussing stress transformations. In blue, from lecture 17, we will be discussing combined loading. In brown, from lecture 18, we will be discussing statically determinate beams. And in lecture 19, we will be studying statically indeterminate beams. I'd like to start off with Moore's circle, which connects primarily to stress, and it is a method of stress analysis. This method is especially helpful when we are trying to find principal stresses and max shear for elements that have both normal stresses and shear. So to start off, it might be best to look at the stress transformation method equations to help get us an idea of what we will be using to solve for the principal stresses made easier through Moore's circle. So the stress transformation method splits up normal and shear stresses using the original direction of the normal and shear stresses to solve for the normal and shear stresses at a plane at an angle to normal. So we start with the normal shear, and we have the normal shear equation above that. One thing to note is that the principal shear will be at a point where shear stress is 0, and the planes of principal shear will be sorry, that should say principal stress. Good catch right there. The planes of principal stress will be at 90 degrees from one another, having both a maximum and minimum stress. So next we look at shear, and we see that there is a max shear. Unlike the principal stress, where you get that there is only stress, at the point of max shear, the normal stress is at average. So moving on to the graphical method, we can see basically this same strategy put into a graph and made easier. So we have a center point, which is located at the average stress. We have a point on the circle, a reference point, which we can call M here, where M is the location of a point on the circle, usually given by the original shear and normal stresses. From there, we can find the radius of the circle and thus find the maximum and minimum stresses. Moving on to 3D, we see that the graph in 3D includes a third stress, which is sigma c, which is the z-plane. And for our analysis so far, z-plane was not accompanied by a shear, so there was still only a single shear, and in that direction, the Z stress was a principal stress. So the effects of looking at a 3D element and considering the Z plane, it can lead to an increase in max shear and an increase in max stress. So moving on to combined loading, which arises from multiple types of stresses. In this case, we will have to consider the torsion and bending moments as well as the shear stresses and normal stresses, sum them up to find the total normal stresses and the total shear. So I've started by giving us again a brief description of what all of these present internal forces are and what type of stresses they create and where those stresses are located. So we can see for torsion, it results in shear, which increases outward, finding its max at the outside or max radius. For shear stress, again, these are all on a circular solid. For shear stress, we see that the max shear is at the center of the circle with having no shear on the top and bottom. For normal stress, for this case, it is uniform. And for bending, we see that it is bending moment. That is incorrect. So bending should result in, I wrote shear, but it should result in normal stress and bending, as we see above. In the bending moment, equation right here. And unlike this graph above, we will actually have a neutral axis, which is a point where there is no normal stress due to bending. On one side, you have the max compression or tension, and then it will be opposite on the opposite side, being the max tension or compression. So that matches the graph below, and we see that at the normal axes, there is no normal stress from bending. Looking now at the superposition, it's what allows us to use all of these different internal forces and find the maximum shear and normal. So with superposition, we can first deal with the individual forces and add them together, acknowledging that each point has its own stress state. It is important to note that for reaction forces, there are one normal and one torsional force, then two shear and two bending forces. A quick look at the element here, imagining that was just an element on a body, and moving over to the equations, which essentially are just adding up the equations which we looked at for the internal forces. All right, moving on to statically determinate beams and statically indeterminate beams. I connected these together kind of, you can see they're all intertwined with one another because there are a lot of the same techniques for solving, except for the fact that when solving statically indeterminate beams, you have to, say there's one additional equation, you must use the equations from bending, the slope and deflection, to be able to find and create a extra equation to solve for the extra unknown. So, sorry, this should be pathing down to the beam deflection, and we see that it is highly related to VM diagrams, and you'll see that we'll use similar techniques when solving these, as we need to find the equation for moment in order to solve for the slope and deflection at different points along the beam. So some important things to note are that we will later plug into our beam deflection equations to help solve for the coefficients is how the beam will be supported. So there are simply supported beams, overhanging beams, and cantilever beams. And depending on the other conditions, these may be statically determinate or indeterminate, depending on what we're given. However, for these cases, we have some boundary conditions, considering that this is the A side and this is the B side, A, B, and that's just A right here. Here we have, there is zero displacement for the YA equals 0. And in the last case for the cantilever beam, we also know that at point A, there will be 0 slope, essentially, because it's not a hanger and controls the moment as well, a hinge. So where we will implement those equations, we can look down to the equation. This is going to be the general important equation. 1 over P, which is the radius of curvature, equals mx over EI. Some quick attributes to note about the equation is that when mx equals 0, the radius of curvature also equals 0. When the radius of curvature is max, mx will also be at its max. All right, so if you take so mx is the second derivative of yx, so we actually need to integrate to get back to the solution for the displacement. So integrating a single time leads to the slope equation, which we have here. Then integrating twice leads to the deflection equation. So you see that this brings up more unknowns with C1 and C2, but we can use these boundary conditions to solve the unknowns and also create an extra equation to solve the equation, solve the beam as a whole in all. I provided a quick graph to help show you what it means by the slope, what it means by the deflection along the beam's length, and then helping to describe the boundary conditions a little bit. Through an elastic curve, when y equals 0, it is resisting displacement, and with theta equals 0, it is resisting rotation, kind of what we discussed up here in the boundary conditions. So that essentially wraps up our course on 131A, excluding the column buckling topic. I've had a great time in the course of this class, and I feel like I've honestly learned a lot that is very applicable to what I do, especially on my club teams here. So I've been super stoked on learning all this information, and yeah, excited to keep moving forward and see how I'll use this in the future. But I've enjoyed the class. I think that these mind maps have been super helpful for me consolidating and collecting this information. So we'll see next week, but hopefully it helps me a bit on the final, and gets a little bit of extra credit, so can never be mad. But If anyone's watching, thank you for watching.